We have a homework on antiderivatives. I'll do as many of these as I have time for. The first one is clearly some power rule stuff, and we're trying to find the thing that when you do the derivative gives us this. Well, we know when we take the derivative, the power goes down, so when we do the antiderivative, the power has to go up. And the way I like to think about it is like I don't actually do any division or anything. I just think, well, when I take the derivative, I know I'm going to multiply by 6, and I have to end up with a coefficient of 1. So I need to have a coefficient of 1/6 here. That way, when I multiply by 6, it'll give me x to the 5th. Another way to think about it on this next one is the power goes up, and instead of thinking about what the coefficient is, we could just take whatever the coefficient already was and divide it by 4, which is 1/4. I always like to check at the end, is this actually going to give me the right derivative? Sure. When I take the derivative of 1/4 x to the 4th, I'll multiply by 4 and lower the power by 1, and it'll work. This one looks like a power rule, but it is not. The derivative that gives you x to the -1, which is 1 over x, sometimes it's written either way, is the natural log of the absolute value of x. And the reason we need the absolute value here is because we can't do the natural log of negative numbers, but we could have had negative numbers here. And so when we do the integral, when we do the antiderivative, we need the absolute value of x. That when we take the derivative, it does give us 1 over x. And the last thing we need is this is one antiderivative, but I can add any constant because the derivative of any constant will be 0. So it could be 1/6 x to the 6th plus 1/4 x to the 4th plus natural log of absolute value of x plus 5. And when I do the derivative, I will get this. So we always put a plus c at the end of our general form. I'd like to do D here. Here we're solving a differential equation, which means that we're finding the function that when we do the derivative gives us this equation. And unfortunately, when we're doing antiderivatives, we don't have any quotient rule or product rule, so whenever you see a product or a quotient, you need to be able to rewrite it. There are two ways to do this. The first thing is you might just think this is x to the 1/2 power, and each one of these is dividing by it. When you divide, you subtract the exponents. So 2 minus 1/2 is, this is still f prime of x. This is 5x to the 2 minus 1/2 is 3/2. Here, this is a power of 1, and 1 minus 1/2 is 1/2. Oops, 3x to the 1/2. And remember, this comes from algebra 1, which is that when you divide two things with the same base, you subtract their exponents. Another way you could think about it is 5x squared plus 3x times x to the -1/2, and when you multiply, you add exponents. So 2 plus -1/2 is 3/2, 1 plus -1/2 is 1/2. And now again, we're going to do the power rule. So I know the power is going to raise by 1, because when I do the derivative, it lowers by 1. So 3/2 plus 1 is 5/2. That one, when I do the derivative, it'll go down to 3/2. I need to multiply by something that will give me 5. This is one way of thinking about it. And so the answer is 1/2. That's so wrong. The answer is 2. That way when I multiply by 5/2, the multiplying by 2 and dividing by 2 will cancel out, and I'll just get 5. Or another way to do it, and I'll do it on the next one, is when you raise the power, you take the old coefficient and divide by this. Well, when you divide by 3/2, that's the same as multiplying by 2/3, and you can see that one also needs to be 2. So 2x to the 5/2 means 2 square root of x to the 5th plus 2 square root of x cubed. Doesn't matter whether it goes inside or outside. And then, of course, I need the plus c because I could add any constant here and it would still give me the same derivative. So this was f prime of x, and so when I do the integral, that's f of x. The original function is this guy, and when I do the derivative, it gives me this derivative function. Okay. And this one's a little bit weird because we've got our derivative and we want to find the original function, and there is no quotient rule for antiderivatives, so we need to rewrite it. And there's a few ways we might think to rewrite it. Maybe this is 3 cosine of x. 1 divided by sine squared is cosecant squared, but we don't know any derivatives that are cosecant times, or cosine of x times cosecant squared. So this doesn't help us. And there's no product rule, so unless we can recognize the derivative, we can't do it like this. Another breakup would be like 3 times cotangent of x, because that is cosine over sine. There'll still be one more 1 divided by sine, and that's cosecant. And this we can do. Cotangent of x times cosecant of x, that is one we should recognize. The function needs to have 3 cosecant of x. And then I always think to myself, what is the derivative of cosecant x? The derivative of cosecant is negative cosecant cotangent. And I don't want it to be negative, so I need to put a negative in the original one. That way when it becomes a negative, it'll multiply to make a positive. And of course I need a plus c. Maybe the original function was negative 3 cosecant of x plus 7. And then when I do the derivative, it'll give me this. Okay. Let's see. Here we've got an exponential. The derivative of 3 to the x is natural log of 3 times 3 to the x. So when you do the derivative of something with 3 to the x, it still has a 3 to the x. So I know I'm going to need a 3 to the x still, because that way when I do the derivative, it'll give me 3 to the x times natural log of 3. If you don't know that the derivative of 3 to the x goes to 3 to the x times natural log of 3, then this won't work, right? You need to know your old derivatives. So if this will multiply by natural log of 3, to undo it, I need to divide by natural log of 3, and that'll go with the constant. I could rewrite this a few different ways, but 5 divided by natural log of 3 times 3 to the x will work, because when I do the derivative, this is a constant, and when I do the derivative of 3 to the x, it'll still be 3 to the x, times the natural log of 3 will cancel out and give me just 5. Here I've got just a 6, and the thing I need to take the derivative of to give me 6 is 6x, plus c, of course. And this was just an integral, so this means do the antiderivative. I think I'll do one more on this page. The integral of 3 sine of t. The reason I want to do this is one that people kind of consistently mess up. The derivative of sine is cosine. The integral of sine is not cosine. The thing that will give me a derivative that's sine is going to be cosine, but think about what's going to happen. When you do the derivative, and we'll just leave the coefficient alone, the derivative of cosine is negative sine. Well, we don't want to get negative sine, so we need a negative here. That way when we do the derivative, it'll be negative sine, and it'll be positive. And then this one, of course, is the integral of e to the t is just e to the t, because the derivative of e to the t is e to the t. You can always, it's always a good idea at the end of doing an integral to think to yourself, if I did the derivative, will it give me the right value? That way you can find, did you find the antiderivative? On the back, I think I'll do this one. This says, do the derivative of the integral of f of x dx. Let's think about what this means. This says, find the antiderivative. Oftentimes we'll use a big f of x for the antiderivative. We'll call big f of x the antiderivative. And then we want to do the derivative of the antiderivative. Well, that just gets you back to the original function. The whole point of the antiderivative is when you do the derivative of it, it gets you back to the original function. Notice how that's different over here. This says do the integral, the antiderivative of f prime of x. Well, this is the derivative. The antiderivative would be the original function, except you also need a plus c, because when you do the derivative of this, it doesn't matter what c is. When you do the derivative, the c will go away, and it'll just get us f prime of x. So remember, whenever you do the integral, it almost undoes the derivative, but you do need a plus c. Okay, I'd like to do c and d here. Let's make sure we remember how to do derivatives. The derivative of e to the something is going to be a chain rule. The derivative of e to the something is e to that something times the derivative of the inside, which is 10x. We usually put this in front. 10x e to the 5x squared. Now it asks you to evaluate this integral, the integral of 10x times e to the 5x squared. Well, we don't actually know the rule yet for how to do this, except that we just literally did this derivative. And so the antiderivative has to be the thing that gives us this derivative, which is e to the 5x squared. When we do the derivative, it gives us this, and therefore we know that's right. We also need a plus c because it could be anything. The last one we need is the second derivative. So if we want to find the original function and we have the second derivative, we do it one step at a time. First we find the derivative. So this is the antiderivative of the second derivative. And this is x, so the thing that will give me the derivative is x squared. This would multiply by 2, and so I need a 3 there. That way when I multiply by 2, it'll give us 6x. Or you could do 6 divided by 2 to get you to the 3. It's fine. The thing that gives me a derivative of 8 is 8x. And so when I take f prime, this will give it to me. And I need a c. The derivative of any of these functions, doesn't matter what c is, will all give me 6x plus 8. Now I can find the original function. The original function, the thing that will give me a derivative of x squared, is x cubed. And when I take the derivative, it will already give me the 3. Or I could think 3 gets divided by 3. That gives me 1. This will be x squared. And I'm going to divide 8 by 2 to get 4. 2 times 4 will give me 8. And this c, the thing that will give me a derivative of c is c times x. That one, when I take the derivative, I'll just get c. And we need another plus c. Now, these c's don't have to be the same, and so we need to give them different names. We usually call this one c1 and this one c2. So I'm going to go back up here and call this one c1. There are two different constants we could have in this problem. We give them different names because they don't have to be the same. If I do the derivative of this one, I will get f prime of x. If I do the derivative of this one, I will get f prime prime of x. Next class, we'll be talking about how to find what these c values are given an initial condition.